All right, folks, let's get started. Today's the last lecture before our midterm on Monday. So a couple of announcements. Please do the Respondus test quiz before our Monday evening exam. Only about 10 of you have done it so far. So on the test quiz, and it's linked in a bunch of places. I think I even put a due date on it for like tomorrow. So I want you to look at it. In that test quiz, the instructions has a link and instructions on how to download the application. Do not think you can just go to the App Store and download it, right? The one that we have that OSU has you download is actually a different one than the one you search on the App Store. So do just follow the directions on that test quiz. It links to the right one. Yeah. You can do it on your computer too. I think in the test quiz that there's a link for downloading it on your computer or your iPad, but I would suggest if you have the choice, I prioritize the iPad. Right? Okay. So yeah, use the link that's in the quiz. Moral of the story. Also, your Wi-Fi should be EDU Roam. IT assures us that if you use EDU Roam, there should be no connectivity issues. Last fall, there was a internet outage in the middle of one of our exams, like right in the middle. I don't know if you heard about that. It was awful. It was midterm 3 for 1210, and we had to give everyone a new version of the exam, open note, open everything, because that internet outage, it never came back. And it was awful. So that's what EDU Roam is here for. So do make sure you're logged into that network. The difference is, I don't know if you like check your phone or whatever, if you're on OSU Wireless versus EDU Roam. OSU Wireless, when you log in, you just put your name dot number, but for EDU Roam, you have to put your name dot number and at osu.edu for it to log in. So that network is much more reliable from what we've been told from IT. And then finally, when you're doing the test quiz and the exam, look for the gray bar at the top of your screen. If you see a colored bar, you are actually not inside Lockdown Browser, you're inside Canvas. So when you're going to take the test quiz, before you put in the password and write test, you should see a gray bar. So you'll know that you're in, Lockdown Browser, go away. All right, details about midterm 1, which is on Monday at 6:30. It's not in this room. It's in CBEC at CBEC 130. So it's the lecture room down there. It's in front of the the hexagon wall, the brightly colored hexagon wall. It's like right there, right? Remember, midterm covers chapters 1 through 4. We're going to finish the last couple slides of 4 today, bringing everything together just in water. And we'll start a little bit of 5, just enough for you to get ready for the lab that's happening next week. And then also know that since we're finishing chapter 4 today, homework for all of chapter 4 will be due on Monday before your midterm is due, or your midterm, time. And so before scheduling this midterm, over this, over winter break, I checked every single one of your guys' schedules to see if there was conflicts. And I think I went through most of them, unless you added late or whatever. And so 6:30 should work for the majority of you. But if you do have does anyone have a conflict? Like another class? Maybe I might have missed you in my search. Okay, so it is expected that everyone takes this exam at this time, unless you have SLDS accommodations. But if you do have a conflict, you fill out a makeup or alternative midterm form, and you'll take it later in the week if you do have a conflict. If you're, for some reason, you miss the exam, all right, like if you forget and you just don't show up, we do have things in place where you can take a makeup. It might not be the same exam your classmates take. It may be given at the end of the year. So just come to the exam. All right, and then my review session is tomorrow at 6:30 in the same room in CBEC 130. Any questions about the midterm? Any questions? Okay, and maybe to continue what we did last Thursday, I have another survey question here. If we prefer questions that are conceptual based or math-based. So when you leave today, you can put a paper clip in the cup that you prefer. If you want an all concept exam, so no math, you don't need a calculator, or an all math-based exam. I just want to see. All right, so if you feel compelled about it, please answer it at the end of class. And I will tell you the results in my recap tomorrow. All right, so let's move on. Oh yeah, chapter 4, that's where we are at right now. So we left off on Tuesday going through the ideas of stoichiometry, all right, where we had mole conversions that we discussed, all right, gram to mole conversions, volume to mole conversions using molarity. So we used molar mass from the periodic table or concentration given to convert measurable things like grams or milliliters to mole amounts. So we did a lot of gram to mole conversions and used stoichiometry, meaning balanced chemical equations, where we went from one substance to another substance using the coefficients that are in the balanced chemical equation, but we have to be in the unit of moles. So about 100 times we went from grams to moles to moles to grams over and over and over again. We used molar mass, stoichiometry, molar mass of the new substance over and over and over again. That's what we did previously when working with gram amounts. But now in solution chemistry, we don't work with gram amounts. We typically work with solutions, volume amounts with a certain molarity. But if we're, aware of this in our ideas of chapter 3, is that molarity just means is a conversion between a mole amount and a volume. So the unit of molarity, let's remember what it is. It's moles of your solute over liters of your solution. So in this example, if I have 8 moles of potassium, all right, so it's my reactant, and I react it with water to produce 1 liter of solution of KOH. So it seems like I'm turning potassium and turning it into KOH. What is the molarity of potassium hydroxide, the product here? So they tell us, a liter amount of potassium hydroxide. So I have the denominator here. All of the potassium hydroxide comes from the potassium that we actually add to the reaction. So to get moles of potassium hydroxide, I need to figure out how much of that potassium actually reacts here. So this is where we use stoichiometry. We start with 8 moles of K. So we're already in moles, so we can get on the bus and use the coefficients here. 2 moles of potassium produce 2 moles of potassium hydroxide. And so in this solution, I should have 8 moles of potassium hydroxide as well. But that's not quite my answer. This question is asking for the concentration. So I need to go one step further and recognize unit of concentration as moles per liter. I have the mole amount. I just need to divide by the liter amount that's present. And so it's just 1 liter, all right, to get concentration. And so we see if we react 8 moles of potassium with water to produce 1 liter of solution, we should get an 8 molarity, or I guess 8.0 molarity KOH solution at the end, all right? So molarity is just a new unit we can use to convert between mole amounts and volume amounts, just like we did molar mass that related mole amounts and gram amounts. All right, so, okay, there are all my announcements. Keep going. Okay, so the rules for solution chemistry, stoichiometry is much like the rules that we talked about previously. You need to work in moles. It's just molarity is the new conversion we have to go from mole amounts to volume amounts. So all the things that we need to work with when talking about solution stoichiometry is the same as before. We need the balanced chemical equation to give us the stoichiometry we need to convert between stuff. We need typically the molarity of the solution that we're working with. Remember, molarity is moles per liter. You went to bed the other night and said it 100 times, right? Molarity is moles per liter, moles per liter. And then finally, you typically need the volume of solution you used, because if you multiply molarity and volume, you get moles of your solute. Just like when we took grams and molar mass and divided them by one another, we got moles. It's analogous here. All right. So I just want you to think about molarity as this new conversion factor we can play with, because then you don't have to learn anything new. It's just a new conversion that we can use. All right. So let's do a bunch of practice problems. So this one is a little bit of a review. So we talked about neutralization reactions in solution chemistry. but I'll give you another example that's a little bit more familiar. So let's look at this chemical reaction where we take 2 moles of HCl, that's a monoprotic acid. We take 1 mole of calcium hydroxide, that's a dibasic base because there's 2 hydroxides there, and then you neutralize it, right, and make water and salt. So this question is asking, what is the minimum mass of HCl in grams required to neutralize this many grams of calcium hydroxide? So it seems like they're giving us an amount of calcium hydroxide and they want us to tell them, okay, how much HCl do I need, right? So this question is actually exactly like the first part of the chapter where I give you a gram amount. I want you to do stoichiometry and you give me another gram amount. So let's just practice again how we do that. So if we want everything in gram amounts, we need molar mass, which I gave you, which is nice. So if we start with grams of calcium hydroxide, I want to use the molar mass of calcium hydroxide given here. So 74.093 grams of calcium hydroxide is 1 mole of calcium hydroxide. So now I'm in the unit of moles of that base. Now I can get on the bus and go and use stoichiometry to go wherever I want to go. I want to go to HCl. So where am I going to put the 2 in the next fraction? So the coefficients here, it's a 2-to-1 ratio. So where am I going to put that 2? On the top or bottom? On the top, yes. 2 moles of HCl is 1 mole of calcium hydroxide. And now that I'm in the unit of moles of HCl, I can use the molar mass of HCl that's given. So 1 mole of HCl is 36.46 grams. Okay, so yeah, what you see here, what we did is we did molar mass, stoichiometry, molar mass. This is no different than what we did on Tuesday. See, but there's a problem here is that yeah, calcium hydroxide is a solid. You can weigh it out, but HCl is not a solid. All right, HCl, this acid doesn't come in the solid form. It's typically in a solution that has a certain concentration. So let's look at an example that's a little bit more believable where HCl is actually in solution. But what you'll see here is that the process is the same. It's just we use a different conversion. All right, so here's this one. What volume of this concentration HCl, so 0.0723 molarity HCl, is required to neutralize the same amount of calcium hydroxide? So this time we're still starting with the same amount of base. We just want to go to milliliters of a solution now. So it's just the end part of this calculation is going to be a little bit different. We're starting it off the same. We're starting with gram amounts of base. So to get to moles of that base, we use the molar mass. We still use the same stoichiometry, but we don't want to go to grams of HCl where we would have used molar mass. We're going to instead use the molarity that's given. And so I always like to rewrite those molarities into an equality that makes more sense to me, because big M doesn't really mean anything to me. So 0.0723 molarity means that there is 0.0723 moles of HCl in 1 liter of solution. And so that will allow me to do the division, the fraction to get to the new unit that I want. So I'm going to start with what's given, which is calcium hydroxide, and we're going to HCl again. We're just taking a little detour at the end. So gram amount, we're starting this off exactly the same. So 74.093 grams is 1 mole of calcium hydroxide. Now that I'm in moles of calcium hydroxide, I can do the stoichiometry. So 1 mole of that base, calcium hydroxide, is 2 moles of HCl, and this came from the balanced chemical equation. Then after that, now that I'm in moles of HCl, the goal here is to get to volume. So I'm not using molar mass here. I am using the molarity that we were given in the beginning of the question. So with this last fraction, where am I going to put the 0.07 part? Am I going to put it on the top or the bottom? Am I going to divide by molarity or multiply by molarity, given the units, what it means? Think think about what unit we're in right now if we cancel stuff. So if we cancel grams, we cancel moles of calcium hydroxide. I'm right now in the unit of moles of calcium hydroxide. So where am I going to put that 0.723 part to get that to cancel? I'm going to put it on the bottom. Yeah. So yes, we are dividing by molarity in this case, but that's not something I memorized. I just try to cancel the unit. So 0.072 moles of HCl and 1 liter of solution. And then you can convert to milliliters if you want. Let's just get the answer. Oh, I don't even have, oh no, the answer is right there. Okay, right there. 0.504 liters. So 504 milliliters is what is required to neutralize all of that calcium hydroxide. All right, so we used molar mass like normal because we started with a gram amount of substance. We still needed to apply stoichiometry, the balanced chemical equation, and then in this last step, we used molarity to get a volume of a solution because we're working with a solution and a solid here. All right, so do you see where we're going now? What do you think the next one is? The next one is now there's no solid. Now it's 2 solutions. This question's asking, okay, what is the minimum amount of HCl? It's the same HCl that's required to neutralize this volume of this concentration calcium hydroxide. So it looks like I'm still given calcium hydroxide moles. I'm given a volume and a concentration. So I'm given all those that information so I can calculate moles. All right, I can use stoichiometry to get to HCl and then use the molarity that's given for that piece of information. So I'm given 2 different molarities here. So I'm going to use the molarity for calcium hydroxide with the volume of calcium hydroxide to get moles, then do stoichiometry, and then use molarity again to get to volume. So see how we detoured those gram amounts. We're not using molar masses here. I gave them to you, but you actually don't even need them because I gave you molarities and volumes. So going through this, so we see our starting point is a little bit different. We have volume of calcium hydroxide. And so do recognize what molarity means. Again, take the time and write out what it means, because then you'll see where the unit needs to go. This means 0.225 molarity means there is 0.225 moles of calcium hydroxide in 1 liter. So where am I going to put the 1 liter part? Am I going to put that on the top or the bottom? Bottom, yeah, because liters cancels. 1 liter of the solution is 0.225 moles of calcium hydroxide. So now I'm in the unit of moles of calcium hydroxide, just like in my previous examples where I used molar mass. It's just I got there in a little different way. I took this detour instead. All right, but now it's the exact same. I still do stoichiometry. So 1 mole of that base is 2 moles of that HCl. I need 2 moles of the acid to neutralize it. All right. And then it's the same as the previous question. So given the molarity of HCl will tell us the volume that's required. So I'm going to put that 0.0723 on the bottom again and 1 liter of the HCl solution up top. And then that's your answer. So about a liter of HCl, oh, I'm sorry, to neutralize all of that acid, or sorry, that base. Right. So again, I like the way I teach solution stoichiometry is for you to recognize molarity is just a new conversion factor for you to relate volume and mole amounts. And it's no different than when we used molar mass to relate gram amounts and mole amounts. That's the new idea here. All right. And the process is the exact same, just different ways to get to moles. All right. How do we feel about that? Okay. Good. All right. So let's look at a couple applications of solution stoichiometry. We're still doing reactions in water. We're just doing slightly different calculations. So you did this in the LLT lab. I couldn't think of the acronym. The lemon juice lab, all right, where you standardized a base solution, so sodium hydroxide, using a standard acid, KHP, potassium hydrogen phthalate, and you were able to weigh out the amount of acid you used in your titration, in your Erlenmeyer, and you dispensed a known amount of base to neutralize it. And using that information, you can back calculate what the concentration of that titrant of that sodium hydroxide in your burette must be in order to neutralize your acid. So in this case, KHP, the acid, is inside the flask, while sodium hydroxide, your base, is in your burette, and you're dispensing a known amount of it. That's a very beautiful pink. I had to search the internet for that pink. All right, so that would be the end point. So, but I just give you all the information here. So I'm saying, okay, a chemist, you dissolve this much KHP, so that many grams, in about 50 milliliters of water. The volume here doesn't matter because we're just looking at mole amounts. And we titrate with sodium hydroxide. That's our titrant. That's the thing in the burette. Don't know the concentration of it, but we know it requires 25.29 milliliters to neutralize it. That's what we know. All right. So when something's neutralized, the moles of acid equal moles of base. So I have kind of a generic chemical reaction here, acid and base. KHP, I'm just going to call HA, meaning it's just something with a proton, an acidic hydrogen on it. So I'm just going to call it HA, because an H plus an OH minus and hydroxide make water. That's your neutralization reaction. So the important thing here is to know that a chemical reaction is happening. So we need to balance this. If we have a monoprotic acid and a monobasic base, what's the ratio of the balanced equation? Just 1 to 1. This is important because it's not always 1 to 1. We always have to recognize a chemical reaction is happening. We don't really care about the products because we just want to relate the two reactants. The products don't really matter here. So this question, given this information, grams of the KHP you put in and final volume of base you added, it's asking what is the concentration of sodium hydroxide in the solution in molarity. And so recall molarity, and in this case, it's sodium hydroxide. We want to know what is the concentration in this burette. Is the moles, the amount of moles of sodium hydroxide present in the solution over the volume of the solution. Always, it's moles over volume. So looking at the information here, do we know the volume of sodium hydroxide we used? Yes, it's given in the question. We know that. We know it's 25.49 milliliters. Obviously, convert it to liters, but we already have the denominator. We know how much we dispensed. Now we just need to figure out how many moles of sodium hydroxide are present in that same sample. And how we get it is by using the mass of KHP that we started with. Right. So this is kind of like, one of the previous questions that we did where we converted like gram amount to a gram amount using molar mass and then continued the stoichiometry. This is kind of similar to that because we're able to weigh out a gram amount of KHP. So 0.7137 grams of KHP. If we calculate, or I'll just call it HA because it's just a generic acid. All right. We are given HA in this scenario, and we can then use stoichiometry to relate it to the moles of base that are present too, because we know how many milliliters required to neutralize it. So I want to use the molar mass of HA or KHP that's given. So 204.22. 204.22 grams is 1 mole of that KHP. But I'm just going to call it HA. Right. So that's your moles of acid that are present in this flask. Okay, and so I know there's a 1-to-1 ratio between acid and base in this specific reaction. So 1 mole of acid needs 1 mole of base, sodium hydroxide. And that is how I get moles of sodium hydroxide to put in the numerator part of that molar or that molarity calculation. So I always like to inspect units, think about, okay, what pieces of information do I already have? What do I need to get from with the remaining information given? So this amount, this mole amount is something 0.00349947 moles of sodium hydroxide is what I dropped from the burette. Okay. is what is required to neutralize that acid, that gram amount of acid. That's what we just calculated, because we know if we add an X amount of acid with a molar mass, we can figure out how much base we need. So that is the numerator. So to actually get the molarity, I'm going to divide that number by the volume that I actually dispensed. So in that case, it's that 25 milliliters, but it needs to be in liters. So divide it by 0.02549 liters. And then that should give me a molarity, and I get something like, oh, the answer is right there. Okay, great. I always forget. Right. Okay. So that you already did that calculation, or you should here really soon for you Thursday lab folks. Part A. This is part A of LLT. Okay. This is similar to part B and C. All right. So titrations. Titrations are a little bit different, because in this example, the acid we put into the Erlenmeyer was a solid, so we used molar mass. But when you put like lemon and lime juice into the Erlenmeyer, is that a solid? No, that is a liquid. So we instead dispense a known amount of volume of an unknown. So like our lemon juice or lime juice or something, we put that into our Erlenmeyer, and then we are titrating with a base with a known concentration. That is what a titration is in this point. So in this example, I'm telling you it takes this much HCl with this concentration to completely neutralize 10 milliliters of sodium hydroxide. So in this example, sodium hydroxide is actually in the flask in the Erlenmeyer, and HCl is in the burette in this case. So that's how much it took to neutralize the sodium hydroxide. What is the concentration of sodium hydroxide in molarity? So again, inspect the units. Molarity of sodium hydroxide will be moles of sodium hydroxide present over the volume of sodium hydroxide you used. Do we know the volume we used? Yes, what is it? Is it the 10 number, or is it the 15 number? The 10 number, yes. The volume of sodium hydroxide is 10.00 of an unknown concentration of sodium hydroxide. So we know the denominator, it's 10 milliliters, so 0.01000 liters. Okay, the question is, how do we get moles of sodium hydroxide? We're going to use the HCl that we dispensed. But remember, a chemical reaction is happening when we relate base and acid. So let's quickly balance that. What's it balanced? HCl and sodium hydroxide. It's just 1-to-1, because everything is just monoprotic or monobasic, so it's just 1-to-1. All right, so just like the previous example. So I'm going to use the known amounts of HCl here to figure out how many moles of sodium hydroxide I dispensed using that stoichiometry, the relationship here. So to get moles of sodium hydroxide, we use volume and molarity of that HCl that's given. So starting with the volume of HCl that we dispense, so 15.28 milliliters of that HCl. I need to convert that to liters. So 1,000 milliliters is 1 liter. I need to do that because the concentration of HCl is, just rewriting it, is 0.2500 moles of HCl is present in 1 liter of solution. All right, so I needed to convert that milliliter to liter. So I'm going to put 1 liter on the bottom here and use molarity 0.2500 moles of HCl is present. So basically all this information just tells me, do all that dimensional analysis. 15.28 milliliters of HCl will contain this many moles of acid given that specific volume and concentration. So that's all we did. We just multiplied volume and molarity together, right? And so now we're in the unit of moles of HCl, but the numerator part we need is moles of sodium hydroxide, right? So we need to do one more step, and it's stoichiometry. So we're going to multiply by what? The stoichiometry. We're right here. We're given HA, but we want to go to sodium hydroxide. So our stoichiometry is just 1-to-1. It's just 1-to-1. So 1 mole of HCl is 1 mole of sodium hydroxide. Okay. And so doing that, you get a new mole amount of sodium hydroxide, and that's going to be our numerator. So the mole amount here is 0.03820 moles of sodium hydroxide is present in that Erlenmeyer flask, right? But that's not our answer. We want to get molarity. And so we need to divide by the volume that's present. So in this case, it's 0.0100, that 10 milliliters. And so we get a concentration, oh, I already have it down there. Okay, is the concentration of sodium hydroxide we started with is 0.3820. All right. So I'd like to group this type of question, this titration question, with our standardization question. It's just different ways we got moles in our numerator if you inspect the units. So I bet half of you are sitting there thinking, I can just use M1V1, M2V2. Is anyone sitting there thinking that? Did anyone in high school, teachers teach you if for a titration, you can use M1V1 equals M2V2? Are you lying to me? Okay. Okay. Or you just are reading the next slide. Okay. Do not use M1V1 equals M2V2 to answer the previous question. If you try it on the previous question, it'll work. You'll get the right answer, right? So in this case, we're solving for like M2, all right, this new concentration of sodium hydroxide, given its volume. We have a volume of HCl and a concentration of HCl. Some students I know have been taught to just use M1V1 equals M2V2, but do not do that, because what you do is you ignore the chemistry that's actually happening, the stoichiometry. The reason M1V1 can work in this instance is because the ratio is 1-to-1. The stoichiometry is 1-to-1. Once it's not 1-to-1, once it's like 2-to-1 or 1-to-2 or 3-to-2, it does not work anymore. So good. No one here uses M1V1 for titrations? You promise me? Think you promised me? Okay. All right. Okay. So then we'll just do this next example then. It's the same numbers here. All right. So we have 15.28 moles of the HCl, and we're neutralizing 10 milliliters of an unknown base. But this time it's not sodium hydroxide, it's calcium hydroxide. So we need to think about the chemical reaction that's happening. How do we balance this? How do we balance this? Yeah, we need 2 moles of acid for 1 mole of calcium hydroxide. So if you try to M1V1 this, you will be wrong. You will be wrong. And so, you know, I don't have any beef with high school teachers. They're given the very hard task of teaching you a lot of stuff in a little bit of time. So I understand that they teach you the tricks, but I'm here to undo those tricks. I want you to learn the concepts and then see, okay, like how the tricks come out of it. So the M1V1 trick only works when it's a 1-to-1 ratio. Once it's past it, it does not work. Do you think I'm going to give you a 1-to-1 ratio on the exam? No, I'm not going to. But I'll have an answer there that is the M1V1 answer, but it won't be right. Okay. So you need to think about the chemistry that's happening. So this question is actually, it starts exactly the same. We know how much HCl we dispensed. It's 15.28 milliliters, and we know the molarity. But the goal here is I want to know how many moles of calcium hydroxide is present in that Erlenmeyer, not sodium hydroxide. So when I do stoichiometry here, it's going to be a little bit different. I need to put 2 moles of HCl on the bottom because of the stoichiometry. This is what we're given. That's where we want to go. All right. And then 1 mole of calcium hydroxide goes up top. So there's this factor of 2 inside this specific example. And so if you calculate the mole amount of base here, it's 0.001910 moles of that calcium hydroxide. All right, but that's not our answer. We actually want the concentration, so we need to divide by the volume. So 0.0100, the 10 milliliters that we worked with, and then that's our answer. So you see here, we're off by a factor of 2. It's the same numbers, I just changed the substance, right? And so the molarity here is just off by a factor of 2. If you used M1V1, you would get the same concentration from the previous slide. You would get the 0.38 number, but that's only if it's a monoprotic acid and base. If it's a 1-to-1 ratio, that's the only time it works. Also, M1V1 dilutions. Dilution is a physical change. Neutralizations are a chemical change. So those should not be, that equation should not be used for both instances. So promise me you will not use M1V1 for titrations. Promise me. Promise me. Because if you're sitting there thinking, I'll just, whatever, Dr. N, I'll just divide by 2. I'll just divide my answer by 2. Well, what if you don't divide by 2? What if you have to multiply by 2? So why not guess and just learn the chemistry, all right, and the stoichiometry behind it? That you're taking a known amount of one substance using stoichiometry to get to the mole amount of the unknown substance. So it's all about inspecting units. So the last one here of application of stoichiometry is calculating the molar mass of an unknown acid or base, okay, in a neutralization reaction. And again, it's inspecting the chemical equation that's happening. So in this example, I tell you, okay, you have this many grams of an acid. All right, so some acid down here, HA, that's in your Erlenmeyer. And you titrate with 21 milliliters of sodium hydroxide with this certain concentration. So that's what's in your burette. And I want you to tell me what is the molar mass of your unknown acid. So I like to just inspect units here. Molar mass has the unit of grams per mole. I want the molar mass of HA, the acid, the unknown acid. So the molar mass of the unknown acid is the gram amount of the acid over the mole amount of the acid. So looking at the information, what part of this fraction do we already have? The numerator, we already have the gram amount, it's given, great. We just need to figure out the mole amount of acid that's present. Do you see, it's the same calculation we did before. It's the same one where we are actually given concentration and volume of sodium hydroxide. We just need to work our way and figure out, okay, how much acid has to react. So it's the same calculation we did previously, all right, where we did the, volume, molarity, stoichiometry. But this time that number is going to go in the denominator. That's the only difference here. But let's keep doing it. Well, first, let's balance the equation. Let's balance the equation. 1-to-1, yes. Okay, 1-to-1. All right, so we are given sodium hydroxide. So I'm just going to convert that to liters right off the bat. So 0.02133 liters of sodium hydroxide. I want to use its molarity to convert to moles. So in 1 liter of that solution, there's 0.1898 moles of sodium hydroxide. Right? But I want moles of HA for my molar mass calculation. Right? So I need to use stoichiometry to get to HA. But you might be thinking, Dr. N, it's just a 1-to-1 ratio. Why do I need it? It's because sometimes you will need to actually put numbers in there. So I'm always consistent. So 1 mole of sodium hydroxide, like in the next slide, it's not 1-to-1. 1 mole of sodium hydroxide is 1 mole of HA. So using the volume and molarity of sodium hydroxide, we can get the mole amount of the unknown acid. So the amount is probably a tiny number, 0.00484 moles of HA is present in that Erlenmeyer, given how much base we had to dispense. All right, that's not our answer. That's what's going to go in the denominator in my calculation. So I need to go one step further here. So 0.4937 grams of HA. That's what's given over what we just calculated, 0.00484 moles of HA equals the answers down there, 121 grams per mole. So I like these, determine the molar mass questions. It's very similar to titration questions as well, I think. You're going from a known volume and molarity of one substance going to another substance, and usually calculating some type of value out of that. All right. So in this example, it's a 1-to-1 ratio. So let's look at another one. So this is the last slide of chapter 4. It's the same numbers. I just changed the substance. So here it says you titrate, 0.4 grams of an unknown diprotic acid with 21 milliliters of base with that concentration. What is the molar mass of the, oh, that says mono, sorry, diprotic acid. So it's the same calculation, basically, but the stoichiometry is different. The chemical reaction is different. So now let's balance this. What do we need? What's the ratio here? 1-to-2. Yeah, so the stoichiometry step is going to be different here, because looking at the calculation for molar mass, it's always grams of substance over moles of substance. I'm given the numerator. It tells me it in the question. I need to figure out the mole amount given all the other information. And since I know the concentration of sodium hydroxide and it's in the volume, I can get moles of the other substance via stoichiometry. So I'm going to be lazy and just copy what we did previously, everything except the last step, because it's that last stoichiometry step is different. At this point, all right, we take the volume amount given, the molarity given for sodium hydroxide. But if we stopped right now, we'd be in moles of sodium hydroxide. We want to get to moles of the diprotic acid. So we need to do stoichiometry. So where's that 2 going to go? On the bottom or top? What? Bottom. Sometimes I hear both and I get scared. 2 moles of sodium hydroxide, 1 mole of the diprotic acid. So we see that the mole amount of acid is half that of in the previous question. All right, where it was just a 1-to-1. And so, okay, what's my answer? So H2A, the moles of H2A that I have is 0.002024 moles of H2A. That's not my answer. That just tells me how many moles of stuff I have in the Erlenmeyer. I actually want to report the molar mass, so it's grams over moles. So I need to take that number. That's my denominator. So molar mass here is the gram amount that's given. So 0.4937 grams equals, over that mole amount we just calculated. Okay, and then there we get our molar mass is the 200 some number. All right, so in this calculation, it's the exact same. It's just we're applying a different stoichiometry. And this is different because I showed 2 examples for titrations and molar mass calculations, right? I showed you a 1-to-1 ratio and then a 1-to-2 ratio. So if you're sitting there thinking, oh, I'll just multiply divide my answer by 2. I'm going to do M1V1 divide by 2, right? I don't know if you'll be right in that scenario, because in this case, we also changed it to a 1-to-2 ratio, but the molar mass doubled in this case versus in this example where we did a 2-to-1, 1-to-2 ratio, the concentration halved. So it's like, will you know on an exam if you do the cheat way to divide or multiply? So the choice is yours. So, but showing you the units of converting using molarity or molar mass as a conversion to go from the gram or volume world to the mole world. So then you can use stoichiometry. That's the big learning objective in this chapter. All right. And so there's basically two different applications of using solution stoichiometry. The first one is titrations. I guess the second one would be standardizing a solution. And then finally, calculating the molar mass of a unknown acid or base. So you just have to inspect the chemical equation, the chemical reaction that's happening. All right, and so I had a couple more slides down here, but that was just, I added them because I thought they were interesting, but they're not assessed on your midterm. And I did not assess you on these for your online homework either. So I'm not going to go over them. So these topics ending right now is on midterm 1. So all of chapters 1 through 4 minus these last 2 slides. Fair enough? But I think chapters 3 and 4, they go hand in hand. They go hand in hand. It's learning about molar masses and molarity, and then using molar masses and molarity in stoichiometry. Okay. Any questions? What topic's the hardest in this for chapters 1 through 4? What? Oh yeah. So the question is, do I have to memorize if it's monoprotic or diprotic? So I want to say it's going to be obvious. Okay, so monoprotic means there's one proton. So I can write it like HA, or I could write something like HCl. Like, can you tell that that's monoprotic? Because there's only one hydrogen, right? Versus, or like HF, monoprotic, one hydrogen. But if I wrote something like H2SO4, is that monoprotic? No, that is diprotic, yes. Or H3PO4, triprotic, yeah. So usually I'm gonna say it's gonna be obvious, okay? Fair enough, okay. Okay, good. Other questions? No? What's the hardest topic? What hardest chapter? One? Yeah? Oh, that's actually, the periodic table is actually chapter 2. Yeah, no problem. Periodic table is chapter 2. So remember, knowing the names of things, because I'm not giving you names on the periodic table. It's just the symbols. Knowing the naming conventions for the different groups and sections of our periodic table. I think I want you to know the names of all the elements to barium, so 56, plus the ones in that period that are common, like platinum, gold, silver, lead, like know those ones too. So everything up to barium, it's not including spelling. I don't mean spelling, all right? Okay. Just like if I say strontium, you'll be able to locate where that is. Can we do that? Yeah. What number is it? And that 38 means what? Yes, so it's the atomic number and the number of protons. Great, so that's chapter 2 stuff. Yeah, naming's rough. It is. There is just stuff you need to memorize. There's no way around it. There's like little tricks and stuff. You just gotta memorize them. Yeah, nitrate, sulfate, chlorate. Yeah, phosphate. Yeah, the rules with the oxygen. Yes. Which ones? Acid-base neutralization? I don't think that's the, yeah, chapter 3. What do you mean? Oh, net ionic equations. Yeah. The thing you need to know with net ionic equations, you're only allowed to split them if they are aqueous and strong electrolyte. So NaCl, is that a strong electrolyte? Yes. If it's aqueous, do you split it? Yes, but what if it's a solid? Do you split it? No, you don't split it. What about HCl? Aqueous, do you split that? Yes, because it's a strong acid and it's aqueous. What about HF? Aqueous, do you split that? No, it's aqueous, but HF is not a strong acid, it's a weak acid. Good. And then just like all straight up solids, you don't split. Yeah. There are 6 strong or 7. Let's just say 7. There's 7 strong acids. Everything else is weak. Let's go through. What are those 7 strong acids? H, Cl, H, Br, H, I. How can, look at the periodic table and think about how you can memorize that. Oh, it's all the halogens except fluorine, all the way down to iodine. So those are 3 of them. What are the other strong acids? Nitric acid, so HNO3. Then we have H2SO4, so sulfuric acid. Then we also have perchloric acid, so that's with the ClO4 And your textbook doesn't say that chloric acid is strong, but it is. It is. So all of those. So that means phosphoric acid. Do you split that in a net ionic equation? No, you don't. All of these things still can be, if it's a weak acid, you can still neutralize it. That's fine. You can still neutralize it. It's just these are the only things that split up fully in the net ionic equation. That's the only difference. Okay. That these substances will conduct a lot more electricity than weak acids like HF or like acetic acid, things like that, that the strong acids conduct way more electricity. How can we tell what strong bases are? What's a strong base? Base means what usually? Hydroxide. So strong bases are typically metal hydroxides. So group 1 and 2 particularly. So any like lithium, sodium, potassium hydroxide, strong bases. Magnesium, calcium, strontium, also all strong bases, but they're dibasic. There's 2 hydroxides per each thing. Go back through the slides, okay, and look for, just click Control Find and the word memorize. Because I usually write, if you have to memorize something, I write it there. Okay. Other concerns about the exam? Okay. So remember, this exam has 30 questions. It does assess each chapter equally. I tried to make it as equal as possible. I would say plus or minus 1 question per chapter, you know, like 7 or 8 plus or minus 1 for each chapter. I would definitely, like if you know you can't do a titration question in a reasonable amount of time on the exam, I would say skip it and do more of the conceptual questions, things that you can just get right away, and not spend a ton of time on those calculation-based ones that you know might take you a while. All right. The idea here is, you know, get as many points as possible that you can get. I don't want you to get to the point where, you know, you spent too much time on like 2 or 3 problems and you can't finish the exam. All right. So there's a little bit of exam strategies here. All right. There's a handful of numerical inputs. And you'll see examples when you take the practice exam, the Carmen practice exam. How many people have taken it? The Carmen one? Yeah, I saw you took it. I saw you. Yeah. Yes. Yeah. Did you take it on Carmen or did you take the paper version? The paper version. Do it on Carmen too, just so you see what it looks like, so you're not blindsided on Monday. Okay. How was it? Okay. Okay. Was it humbling? It was humbling. Okay, great. All right. Everything's free game on the exam. I had Matt check over it, so yeah. Goofy.
Will the numerical input questions be weighted differently?
No, that's a good question because I think this relates to exam strategy. The question is, are numerical inputs weighted more? No, everything's weighted equally. So if I ask you a question like, how many protons does nitrogen have? That's worth 1 point. An empirical formula question is also 1 point. So that's what I'm meaning, like divvy up your time smart, like in a smart way. All right. No, if I asked you how many protons were on nitrogen, it would be multi-part probably. I'd give you a isotopic symbol and I would ask all of the subatomic particles for like nitrogen 14 or something like that. Yeah. But see, like a question like that, it's going to take you no time versus a full-blown empirical formula question. Unless you can crank those out. I don't know, unless you can, if you just practice a bunch of them, you'll see it's the same thing over and over. If you learn my strategies. Okay, anything else? All right, we're gonna move on to chapter 5. Okay, I promise I'm not gonna assign any homework for chapter 5 over the weekend, but this does mean that chapter 4 homework is due before your midterm. Yes, yes. Okay. All right, so chapter 5. And then I'll blow stuff up later. Yeah, maybe not blow stuff up. Okay, since we just finished talking about stoichiometry, okay, how do we use a balanced chemical equation? How can we go from mole amount of one thing to mole amount of another? Okay, we have to be in the unit of moles, right? In order to use the coefficients, the ticket to get on the bus, we need to be in the unit of moles. So I'm gonna skip ahead to the middle of chapter 5. This is slide 19. Slide 19. I'm gonna skip ahead because we just talked about, you know, using molar mass and molarities to get to moles of reactants and products. Here's a new way we can use to determine mole amounts of gases, is the ideal gas law. All right, so gases are a little bit different. You know, solids, we can weigh them, use their molar mass to get moles. Solutions, we can take their molarities, their volumes, get moles. Gases are a little bit different, where we need to know their pressures and their volumes and their temperatures, and then we can get moles. This chapter is very much plug and chug, all right, where PV equals nRT is just another way we can get moles of gases. N is meaning moles of gas. So that N value here, this is important. I want to start on this part of the chapter because it'll help you with gas next week, because you're going to be producing gases and figuring out what chemical reaction's happening. All right, so P means pressure, V means volume, N means moles, R is a constant, it's the gas law constant, and it's written right here, and T is temperature. You will always be given R on exams. No, there's actually 2 R's. There's actually a lot of R's, but as chemists, we only care about 2 of them. So the one R that we use for the ideal gas law is this one. So R equals 0.8206 liter ATM mole Kelvin. We use this R and specific units of pressure, volume, and temperature. If we make sure our pressure in this equation is always in ATM, volume is always in liters, temperature is always in Kelvin, then this is the R that we use. So whenever you plug numbers into PivNert, we need to have our units match, okay? I love equations, but equations are like vending machines where you can't just put whatever you want in the vending machine, right? Like you have to put US currency into it, or what? The machine's gonna spit it out. You can't have crumpled up bills when you put it in the vending machine, because what's gonna happen? It's gonna spit it out, right? And so in order to properly use these equations, all right, we need to massage the numbers before we put it in. So the way we do it is make sure our pressure is in ATM, volume is in liters, temperature is in Kelvin. So when we use this R, we get N moles back out. All right, and there's a conversion we'll look at with pressures here. So I want to do a couple calculations with this new way we can calculate moles. All right, so here's a typical gas law calculation. So using PivNert, let's consider a 12 grams sample of helium. We put it in a rigid 5-liter gas cylinder. This cylinder will explode if the pressure inside exceeds 20 atm. So at what temperature in Celsius will the cylinder explode? You ever think about what would happen if you threw like a can of spray paint into a fire? No, you never thought of that? Yeah, I think about those things. And so the PivNert can solve for it. If we know the pressure required to break the seal of a spray paint can and you throw it into a fire, right? Increase the temperature, at one point it's going to explode. So let's figure out what temperature is required. So they give us a gram amount. They give us a volume amount. So it's kind of just like collecting all of our variables. Okay, so there's my volume, 20 atm, there's my pressure. And it's asking for a Celsius temperature. So that's what it's looking for here. So when we use PV equals nRT, we have pressure, we have volume, we're solving for temperature. R is a constant, so we don't need that. But N here, we don't quite know, but we do. Although I didn't give you moles outright, I gave you a gram amount. And so remember, gram amounts of substances, we can easily convert to mole amounts using molar mass. So if you use the molar mass of helium from the periodic table, 12 grams of it is equal to about 3 moles of helium. So this is the N value in PivNert. So now it's just plug and chug, right? We plug and chug. So P, V equals N, R, T. We have pressure, we have volume. Now we have N. R is a constant. We're just solving for T in this case. So pressure is 20 atm. So cool, I don't have to convert that or anything. Volume is 5 liters. Equals N. We just calculated that from the gram amount. So yes, 2.998 moles of helium. R is 0.08206 liter ATM mole Kelvin. And then our temperature, that is what we are solving for here. So when we solve for temperature, what unit is it going to have? Kelvin, yes. And then we'll have to take it one more step to our Celsius temperature, right? And so the reason we are very stingy with the units of pressure, volume, moles and stuff is because of the unit of R. R is, in this form, is liter ATM mole Kelvin. If you Google gas law constant on Wikipedia, you'll see like 80 numbers. They're all actually the same number, just with different units. It's easier to just convert everything to fit this unit than memorize a bunch of different R's. I promise. Okay, so you solve for temperature, that's what you get. So 133 degrees Celsius is when this cylinder will explode. I don't actually know when a spray paint can will explode. Okay. All right, so another one. Homework's not due, I promise, not due. We're not doing 5 until after the midterm. So let's calculate the number of molecules in a deep breath of air, which has this volume at this temperature and this pressure. So we're using PivNert again. They give us pressure, but it's in torr, so we're gonna have to do a small little calculation before we put that pressure in. They tell us the volume and they tell us the temperature. So here we're solving for N, moles of gas in a deep breath of air. And so this question is asking for molecules, so we can take one additional step to go from moles to molecules. How do we do that? What number is required there? Avogadro's number. Oh, you need to memorize that number. I don't think I gave it to you. Yes, that is what you do need to memorize, that number, Avogadro's number. So let's get it. What is Avogadro's number? 1 mole of anything is the 23, 6.02 times 10 to the 23. Yes. Actually, let me just check real quick. Did I give it to you? No, I didn't. No. Okay. And remember this, that helpful information packet is already posted online, so you'll know exactly what you'll get. Where are we gases? Okay. So we're just solving for N in this case, and then taking it one step further to get to molecules. So 37 degrees Celsius, we need to convert that to Kelvin. We need to straighten up all of our dollar bills before we put it in our vending machine. I think it's 310 Kelvin. All right, and we need to convert that torr amount to atmospheres. All right, so if we divide 375 torr by, 735 torr by 760, we should get our ATM value. So I'm just going to plug in everything. So PV equals nRT. Pressure is 735 over 760, right? And that will be ATM. Volume in this breath of air, this is big lungs, 2.24 or 25 liters. Equals N, that's what we're calculating, moles of gas present to fill that volume. R is 0.08206 liter ATM mole Kelvin, and then finally the temperature, 310 Kelvin. And so if you solve for N here, oh, come on. You solve for N, you get, given these conditions, that that air sample will be 0.0855 moles of gas. All right, but that's not the answer. That's just the moles of gas present to fill that container. So to go one step further, we use Avogadro's number. 1 mole of anything is 6.022 times 10 to the 23 molecules or particles, however you want to think about it. All right, so if we actually went into that breath sample and counted all of the particles, that's how many you would count, a lot of them, right? So in this case, we were given different conditions. We just solved for N in this case, took it one step further. So the last thing is I want to connect it to stoichiometry now. because the ticket to get on the bus of the coefficients on our balanced chemical equation is to be in the unit of moles. So if we have gas samples and I give you a pressure, volume, temperature, that's another way to get moles. Let's think about all the different ways we got moles. Grams, we can use molar mass to get moles. Volumes, we can use molarity to get moles. Now this new one is we use Pivnert to get moles to do stoichiometry, but specifically for gases. So airbags are composed of sodium azide, which composes to give sodium and nitrogen gas. So it looks here, 2 moles of sodium azide gives 3 moles of nitrogen gas in this decomposition reaction. So let's say if 12 grams of sodium azide is placed in an airbag at STP, oh, I forgot to define that. STP means standard temperature and pressure. So that means it's just the lazy way of saying the pressure is 1 atmosphere and the temperature is 0 degrees Celsius or 273 Kelvin. Okay, it's just easier to write 3 letters than all that stuff. So we say STP. It just means 1 atmosphere and 0 degrees Celsius. Okay, so sodium azide, you put it in an airbag. And what is the final volume of the airbag when it decomposes? So when we think about this reaction, all right, when that sodium azide decomposes, the majority of the volume is coming from the gas that's being produced. I know how many grams and moles of reactant I put in, I can calculate how many moles of gas I produce. But the moles of gas isn't important here. We don't stop there. We go on and insert that into Pivnert to figure out, okay, what volume does it take up? All right, so here's just a new way we can play with mole amounts. This strategy should look similar. Grams to moles. We've done that a billion times. We use molar mass of sodium azide. I even give it to you. Then we go from moles of sodium azide to moles of N2. What do I need to do between that step? Moles of sodium azide to moles of N2 gas. Stoichiometry, yep. So we use the coefficients and then we take that mole amount and that's the N value in Pivnert. So that's our strategy here. So let's do it. So grams of sodium azide, so 12.0 grams of sodium azide decomposes. So let's convert that to moles. So 65 is going to go on the bottom, is 1 mole of sodium azide, NaN3. Okay, but I want to get to moles of the gas because I want to figure out how much does the gas take up. So I use the stoichiometry here. 2 moles of the azide, NaN3, is 3 moles of nitrogen gas. All right, so that tells me that if all of that sodium azide decomposes, I should produce 0.277 moles of N2 gas. That's not my answer though. I don't know how much that much gas takes up. And now I need to apply Pivnert here to figure out, okay, what volume does it take up? So the other pieces of information that was given is the pressure and temperature. So this is my N value in Pivnert. I already have pressure and temperature. Now I just need to solve for volume. So pressure is 1 atm. So I'm just doing Pivnert, PV equals N RT. I'm solving for volume equals that N value. So 0.277 moles of nitrogen gas. Oh, do I care about how much sodium I make? Sodium? Why don't I count that? Why don't I count the moles of sodium? It's a solid. So is it going to take up a lot of volume? No, it's not. It'll be a little bit, right? You'll make a little bit of that solid, but not enough to make a difference in the large volume that the gas makes. Times R, this is the same R, I just don't feel like writing it, times 273 Kelvin. All right, and so you solve for volume here, and oh, that's what you get. You get 6.21 liters of volume. So if you put, in your airbag on your steering wheel, isn't that crazy to think? In your steering wheel, there's about about 12 grams of sodium azide in your steering wheel, right? And when it's triggered, it will generate that volume of gas to fill your airbag to, cushion any damage or cause more during a crash. And so it's that production of a lot of gas really quickly, because 12 grams isn't that much, right? 12 grams, that's like 12 paper clips. That's not a lot of solid, but it's making a butt ton of gas in this reaction. All right, and so it's 6.21. Great. So to relate this to your lab, okay, so the answer we got is if all 12 grams of that sodium azide decomposes, we should get 6.21 liters. But let's pretend you did this experiment, right? You detonated 12 grams of sodium azide, but what if you only recover 5.6 liters of the gas? What then? What does that sound like? The theoretical is 6.2, but you only get 5.6% yield. Yes. All right. So we could then go and think, okay, you know, the percent yield will be 5.60 over 6.21 liters. And we'll get like, oh, okay, I was only about 90% good enough to recover. Like I could only recover 90% of it. So this is what percent recovery is. Just think about it like percent yield. Right? What you actually get versus what you calculate you should get. Because that language in the lab manual confuses students, but then I just tell them think percent yield and they go, oh, okay. And then it makes sense. So think about percent recovery like percent yield, where we have actual, that's what you actually collect in lab over theoretical. So you will use that percent recovery calculation and concept in parts A and B of the gas lab, because you are doing a reaction that generates gas and you're collecting the gas in a weird vessel, okay, that you will design. Oh yeah, be prepared to get wet next week. So you're going to collect the gas. But the thing is that this apparatus is not perfect. You're not perfect. So yes, if this reaction generates gas, you might not collect all of it. So the first reaction, the first part of this lab, part A, you're going to figure out what is your personal percent recovery. I think you're going to do this with a lab partner. Did anyone do the pre-lab? Do you do it with a lab partner? Yeah, okay. But you still collect your own data, but you do it with a lab partner. So you collect your gas and you compare it to what you should have collected, and you get a percent recovery. Then in part B, you study a different reaction using the same apparatus, and you assume that your percent recovery stays the same. So you'll compare what you collected actually and relate it back to a theoretical, all right? So that's in parts A and B, you use the percent recovery. But in part C, you're going to assume your percent recovery is 100% because your collection apparatus is different. It is a Ziploc bag. So you do the chemical reaction in a Ziploc bag. In theory, you should not lose any gas, right? If the reaction is completely contained in the Ziploc bag and like you like keep everything separated and then last minute you like drop the thing in, right? All of the gas should be in the Ziploc bag. So you're going to assume percent recovery of 100%. So that's like the biggest thing in this lab. You're going to use PivNert, all right, over and over again. You'll collect your gas sample and measure how much you collected. Yeah, you get a lot of gas. So we have a couple more minutes. So I'm actually going to go to the beginning of the chapter and just think about conceptually what gases are. We've talked about a lot of different types of reactions of substances. You know, solids reacting with gases, solution chemistry. So let's just focus on gases here. I want to talk about pressure because it's some straightforward units that we'll talk about. And we'll look at some historical events that have happened that chemists were able to relate phenomena of behaviors of gases. All right, so let's just use our intuition a little bit here. Okay, think of a gas. Okay, what gas are you thinking about? Air. Okay, good. Okay, that's a good gas. All right, is that a homogeneous mixture or inhomogeneous or heterogeneous mixture? What do we think? Homogeneous, very good. Okay. All right, is a gas sample mostly empty space or packed particles? Empty space, yeah, we can walk through it, okay? We can walk through air. We're not like walking through Jell-O, right, where it's packed. Are gases rigid or easily compressed? Easily compressed, great. Is there limited motion in gases or unrestricted motion? Unrestricted. Yeah, those particles are moving around like crazy. And then finally, think about the particles. They're moving around like crazy. Do you think there's strong attractions between the particles or weak attractions between those particles if they're bouncing around each other like crazy? Weak attractions. Yeah, because if they were packed together, they're close together, it would be strong attractions, but because they're far away, it's weak attractions. All right, good. So we're using our intuition there. All right, next, let's look at this particle description of a gas thing. Okay, we're turning liquid water to evaporated gaseous water. What does the particle diagram look like? So here I have the particle view of H2O liquid. What does H2O gas look like? A, B, C, or D? C, yes. What is special about C? The particles are still like bonded. They still have their chemical bonds. They're just further apart. In A, B, and D, we actually broke bonds in the actual water particles. Remember, going from a liquid to a gas, boiling, is a physical change. It's not chemical. You're just changing the distance between your particles. You're not actually breaking any bonds. All right. So good. So there's our intuition. Thanks. All right. So gases that we interact with. There's a number of elements that are gases in at standard temperatures and pressures. Some of them are monoatomic, some of them are diatomic that we see, like oxygen, nitrogen gas, diatomic, hydrogen common. There's also some common gases at room temperature that are molecular. So compounds like CO2, carbon monoxide, all of these substances, what they have in common are that they're low molecular weight. And we'll see the significance of that later. So they're all molecular compounds and they're fairly light. So light molecular compounds typically make gases is the important thing here. So like something like NaCl, sodium chloride, when you think about that, that's a solid at room temperature and pressure. And it's because there's strong attractions between the particles themselves versus in these lightweight molecular compounds, there's very weak intermolecular forces between them. So that's the big difference here. And we'll go into more detail at a later chapter looking at that. But yeah, molecular compounds, light molecular compounds, typically gases. And then these elements are gases. Some of them are diatomic. Okay, let's think about a misconception. All right, think about blowing up a balloon. If we blow up a balloon, think about blowing up a balloon. How does the volume change when we blow up a balloon? Goes up. Yeah, good. Okay, we're filling it up with helium gas. So yeah, it goes up. Yeah, the volume goes up. All right. What about, how does the mass of the balloon change? How does the mass of the balloon change? You fill up a balloon with helium. Yeah, this is tricky. Yeah. What do we know about helium balloons? They float. Yes, but they float not because they lose weight, but it's because they're less dense than air. Think about it. How did I, like if you blow up a balloon, why does it get bigger? Because you're taking the particles in your lungs and you're putting it into the balloon. So if you're blowing up a balloon, you're putting particles into it. You're putting helium particles into it. Does helium weigh anything? Yes, it does. So when we blow up a balloon, even if it's with helium, the mass does increase because you're literally putting helium in it. So don't let your biases misguide you here. Yes, I know helium balloons float, but it's not because they weigh a negative amount. No, it's because they're less dense than air. It's the density difference that makes it float. But the mass of the balloon does increase because you're adding helium particles into it. Whether it was the air in my lungs, if it was nitrogen gas, whether it was CO2 gas, it would still weigh something. And in helium, it just so happens that one floats. All right, okay. So we'll just end right there and we'll talk about unit conversions on Tuesday. Okay, I'll see you on Friday. Oh yeah, vote whether concepts or math.